Hello everyone, this video is about how to formulate a cDSP using DSIDES. cDSP is a compromised decision support problem, and it's a decision support problem that with a lot of complexity, such as continuous variables plus integer variables, linear constraints plus nonlinear constraints, and multiple goals. We can have linear goals and nonlinear goals. So the benefit of using cDSP is in my previous video. You can check it out. There are 4 parts of a cDSP. We define the given, find, satisfy, and then minimize. So in the given part, we define the system variables. We have 3 of them. 2 of them are continuous one. The other one is, the third one is integer one. And then the deviation variables, we have 2 goals. So we have D1 minus and plus and D2 minus and plus. D1 minus measures the underachievement of goal 1, and D1 plus measures the overachievement of goal 1. Here are them. And D2 as well. So the target of goals, actually we give them goal 1 as 3, goal 2 as 1, which means in the function of the goal, for goal 1 we want to achieve it as 3. For goal 2 it should approach 1. And then in the find part, we define the variables we want to search the value. Here are the 3 systems variables, and then all of the deviation variables here are the variables that we want to look at their value when we achieve the goals. And then we define the goals, constraints, and bounds in the satisfied part. First of all, the goal formulation is like this. For linear goal, it's simple because Ti is always a constant value. It's still linear if we use this formation. So it's a goal function over its target value plus D minus and minus D plus equals to 1. In this way, we approach the target of a goal as best as we can. And then we define the constraints. The first should be the linear constraints, and after that should be the nonlinear constraints. We have 5 of them. 1 of them is linear, 4 of them are nonlinear. And then after those things, we also need to define the deviation variables and the weights constraint. The weights are used to linearly combine the multiple goals, and the sum of the weights should be 1. And the deviation variables, because we can either underachieve a goal or overachieve a goal, we cannot do both. So for a goal, the product of D minus and D plus should be 0. And bounds, we define the systems variables bounds, and then the deviation variables bounds, and then the weights bounds. And we minimize, because in this problem we just want to use the weights to linearly combine the multiple goals by minimizing their underachievement and overachievement. So we define it like this. Okay, let me show you how do I formulate this problem. First of all, you can install DSIDES in your own PC or use our server to run the cDSP. You need to have a folder like this. These are the important files about this model, and this is the Word form of this model. And for these files, because the name of the model is press, we have these documents are very important. First, the data file. Using this file, we define the linear equations and basic information of the model. And then is the function file. In this file, we define the nonlinear equations of this model. And then when we run this model, all the results are printed in this output file. And then some details of the results and running process are stored in these 3 files. I seldom look at them, but if anything wrong, I want to check out the error, we need to look at those files. So first of all, let me open the data file to formulate the linear part and basic information of this model. So in this file, actually a lot of things are defined as the default value. We only look at several things that are important to us. First, this block named PTITLE is the problem title. We can assign a title to the problem. Anything is okay. And then the second block is about the number of system variables. The first one is the number of continuous variables or real variables. The second one is the number of binary variables or the Boolean variables. The third one is the number of integer variables. In this problem, we have two continuous variables, x1 and x2, and then a binary variable or integer variable. I like to use integer variables because actually they are the same, but integer variables include these binary variables. So I don't use the binary often. And then the third block is the systems variables definition. The first column is their name, and the second column is their serial number, number 1, variable number 2, variable number 3, and then this column is their lower bound, and this column is their upper bound, and the last column to the right is the starting point. For any nonlinear problem, because we need to linearize the problem using the starting point, so this point is very important. What if this point is wrong? What if this point allows us to make us stuck into a local minimum? There is another block, explore. Later I'll introduce this in this video. And then another block is the number of constraints and goals. We need to define each type of constraints and goals separately. The first one is the number of linear constraints, as we have one linear constraints, we define it 1. And the second number is the number of nonlinear constraints. So we have 4 of them, so here's 4. The number 3 is the number of nonlinear inequality constraints. So this one is the nonlinear inequality constraint, and the third one is the nonlinear equality constraints. We don't have any here, so it's 0. And the fourth one is the number of linear goals. So we have 1 here, goal 1. And then this one is, the last one is the number of nonlinear goals. We also have 1, so this is 1. And the next block named LINCON is the definition of linear constraints, because we only have 1 here. We list it here. So this part is the name of this linear constraint, and this part is how many variables consist of this constraint. We have 2 of them, x1 and x2. And anything in this file after a colon of a line is some description of something. And the next line, we define the serial number of these 2 variables and the coefficient of them. Here is 1 x1 plus 1 x2 less than or equal to 3.5. So if it's greater than or equal to, this part is GE. If it's equal to, this part is EQ. Very simple. And the next block is the definition of linear goals. We also have 1. This part is the name of the goal. This part is the serial number of the goal. And this part is the number of variables consist of this goal. We have one linear goal as 2x1 minus subtract x2, and approach target as 3. So the right hand side value is actually 3. So we define it like this: 2x1 minus 1x2 to approach 3. And we have a description here. It's a right hand side value. Then the next block is the definition of the deviation function, the z. Minimize here. Because we have only 1 level of this problem, we define it 1. If we have 2 levels, that means we achieve the first level goal as best as we can. and then allow a tolerance. Within that tolerance, we achieve the level 2 goals, and so on and so forth. This problem, because it's very simple, it only has 2 goals. We want to use weights to combine them, linearly combine them, so we only have one level of these 2 goals. And after the definition of the number of the level, we define each level. Level 1 with 2 goals, and description is 2 goals with 4 terms, because each goal has 2 terms, D minus and D plus. And here we define the 4 terms. So minus 1 means D1 minus, plus 1 means D1 plus. And the second value of this in this apprentice are the weights. This means the W1 is 0.5, W2 is also 0.5. If you want to change the weights, we can into W2 0.4, W1 0.4, W2 0.6. So we just simply change it like this. Okay. So if we want to only solve one goal at a time, so it should be 1, 1, and then 0, 0. The next block is defining the stopping criteria. There are 5 numbers of them. The first number is the perform a calculation or just a dry run. 1 means calculation, 0 means dry run. Dry run means if you want to check this model is right or wrong. If it's wrong, some definitions are wrong, it will return some error. So you can set it as 0 to check out if there's any error. But actually I don't use this because if it has error, you just run the real calculation, it also can return it. The second number is if you want to print just the final result or the results of every iteration or synthesis cycle. I just want to look at the final result, so I set it as 0. If you want to look at every synthesis cycle's result, you can set this as 1. The third number is the maximum number of synthesis cycle. You can set it as 20, 30, 40, 50, 100, and 200. The the higher the value here is, the running speed, the lower the running speed, the slower the convergence is. And this number is the desired stationarity of deviation function, which means if after several synthesis cycles the deviation function's achieved value change within this percentage, not percentage, change with this means 0.5%. Yeah, then we assume that we reach to a convergence. And the last one is the desired stationarity of systems variables, and the default value is 0.005. And then the next 2 blocks, we define the name of the nonlinear constraints and nonlinear goals. We have 4 nonlinear constraints from goal 2 to goal 5, from constraint 2 to constraint 5. We define their names here, and this column is the serial number of the constraint in the cDSP, and then some description. But we don't actually define their equations in this file. We define the details of the equations in the Fortran file. Okay, let me go back to the data file and go through everything. And then let's jump to the Fortran file. And then the name of the nonlinear goals, we have just 1. Its name is goal 2. So all the names in this file should not exceed 6 characters and do not allow space in between. You cannot define it like this, but you can define it like this. Yes. And this number is the serial number of this goal in this cDSP, and some description. And this part, ALP out, defines what information you want to input and output. If you set everything as 1, you want to output everything. So I just use the default setting here. That's enough for me to look at the model behavior. And this part is there any variables you want to fix its value? You don't want to search or solve it as a variable. You just fix it as a parameter at first. Here we define a number of the variable. For example, if we want to fix x2, so we want to fix one variable, and the variable is number 2. We define it like this. If we want to fix number 2 and 3, then here is the number of 2 variables, and here is 2 and 3. In this way, we can explore the sensitivity of the model with each variables. You want to look at which variables contribute more to the results. So you can fix some variables and look at the rest here. But in this problem, it's very simple. We only have 3 variables. We don't want to fix anything. We just set it as 0. And the next block is the explore I mentioned before, to explore the starting point. This allows us to try to avoid stacking into a local minimum, because this number is the number of starting points we generate randomly, and then we return 8 best results, and then we print the result. If this is 0, then we don't want to print the best 8 points. And here is the number of integer seed for a pseudo-random generation, and this number is usually slightly higher than this one. And here is the number of variables. Again, we fix. Again, it's 0. And the rest of the files are all default. We use default value, but I want to explain. Here, the flags, we set what things we want to print out from the results and what we don't want. And in this OPT-IMP is the optimization parameters. The first one is how much percentage of the violation we allow for the constraints. If it's minus 0.01, it means we allow 1% of violation. If we want to don't want to allow any violation, we set it just as 0. It's usually a negative value. The higher the value is, the more violation we allow to look at the results. And here, the second value is the reduced move coefficient. So this is a step size that we use this step size to linearly combine the starting point with the solution point of each synthesis cycle. The default value is 0.5, and this is very important. And we use parameter learning. In another paper of mine, I use parameter learning to learn the mathematical relationship between this value and the model behavior. The model behavior includes optimality and robustness and computational complexity of the problem. And this last is the perturbation step for linearization, specified as a fraction of the variable range. So these two, the range is from 0 to 1, and it's a percentage value. Okay, so that's all for the data file. In the same folder with the same name, we have a Fortran file. In the Fortran file, we define the nonlinear part of this problem. So we define 2 more variables, parameters here, F2 and T2. This is to simplify the formation of the goal later. And we need to have the link between the variables in this file and the variables in the data file. So we use x1, x2, and x3 again in this Fortran file. And those are the 3 variables in the data file. So the link is built. Then we define the, in this part, we define F2 function like this, and then we assign the value, set the value of T2. After that, we define all the nonlinear constraints here. So the second constraint of the cDSP becomes the first constraint of this file, because we number the constraints again just independently in this file. But we want to know that the constraint 1 in this file is the constraint 2 of the cDSP. So this is the description. So we define the 4 nonlinear constraints. After that, we define the nonlinear goals. We have only one, so it's goal number 1 in this file. Again, it's the goal number 2 of the cDSP. So it's F2 over T2, subject 1. Okay, that's all for the formulation. And then we go to CMD and go to the folder of the model. So the folder of the model is this folder. So we copy and paste the path and go into this folder, and we type run ALP space press. Press is the name of this model, and enter. So here it shows all these files are generated. It means the model is run well, and we got some results. So let's open the output file to look at their results. So it's like this. To the end is the best results in all the synthesis cycle returned as the best result. So in this result, we see that the current point is feasible, priority level 1, because we only have one level. So this is the weighted combination of all the deviation variables here. So it's pretty good. But for goal 1, the D1 minus is 0.52, which means we achieve the target of goal 1 approximately as 48%. And for goal 2, we achieve about 51%. Yes. And if we go up, yeah, here are the systems variables return value. X1 is this, X2 is this, X3 is this. Yeah. So that